So we're recording. Okay, so the 5 basic types of questions that we're gonna have. When I say energy and torque here, what I mean are those pulleys and blocks with inclined plane. We'll go over that today. We went over that on Thursday with energy. We're gonna go over it today with torque. The truck problem that we went over on Thursday, where the truck came down the hill, this is also the type of problem like the skier in homework 5 or 4 that jumps off the thing, or there's a few problems in 4, but basically where you just write down the energy at A, B, and C, D. You might have some friction, but in general, you just write down the energies and you're good on those. Collisions, super easy. This is just the either elastic or inelastic. And then finally, and I guess with my chat open, just so you know, if you send me a private message, it's going to show up. I'm sorry, Calvin. The equilibrium type problems that we're going to talk about today, there's only 2 types of those, what I call a ladder problem and what I call a scaffold problem. And we'll talk about that today. And then the final one that isn't so much represented in our exams, but ballistic pendulum type problems. What I mean by that is I mean a problem that combines energy and, say, a collision. We'll talk about this at the end. They're super easy to do, but they just combine like collisions and energy. So I guess I should say here that with collisions, we could also have impulse, but impulse is super easy. You should know from your lab. The force times time is equal to the change in momentum. Basically just like that quiz that we did. So any questions on what might be on the exam?
Will you give us the equation sheet with because right now I feel like there's a lot of different equations. Are you going to give that to us or should we prepare that beforehand?
I would prepare my own, but I will give you one. The problem with me giving you one is it's not organized. It's organized how I think it should be organized. And you may organize it in a total different way. The other problem is some of this stuff, like doing a torque and doing a torque diagram, you just have to know how to do it. And I can't really explain that on an equation sheet. But yeah, I'll give you the types of energy. I'll give you the collision equations, but you can also use your book. So if you know where the equations are in the book, there's only a few that you really would probably need to look up. I'm sure you guys know all the energy types, right? mv squared over 2, kx squared over 2, mgh, I omega squared. You'll have your book so that you can look up moment of inertias, but I'm going to tell you straight up, you really only need to know the pulley is mr squared over 2, point mass is mr squared, and what's the other one that you might need? Rod through its center or about one end. I'm not going to have anything weird on there. And at most, you might have to combine the 2 somehow with parallel axis. But even then, I'll walk you through that. So yeah, it'll have equations on there if you need them. But this is really all about knowing how to do these problems. The equations, I think, are pretty simple. So yeah, there'll be an equation sheet. Any other questions?
The collision, is it only going to be in 1 dimension or is it possible 2-dimension collision?
So there is a 2-dimension one on one of the tests. And I mean, the deal with that is that even if it's 2-dimension, you just break it up into 1 dimension. So my thought is, no, I won't do 2 dimensions. I don't think it's particularly different from a 1 dimension. What you learn in a 1 dimension, you learn in a 2. The only thing that you have to do in a 2 that's different is you have to figure out the final magnitude of the velocity and maybe the angle that it's at. So I don't want to say no. I haven't finished writing the test, and I was thinking of a problem that might have a 2-dimensional, but I'm not particularly happy with that problem. I don't think that it's particularly instructive or reveals that you know anything. So we can say straight up, oh, and I should say this. So no two-dimensional collisions. I'll make sure none of that. We're not going to have springs on this. So no springs. I'm not going to make you figure out a spring at all. Don't forget about springs because we're going to do springs when we do oscillations, but we'll deal with that down the road. So you won't have like the problem where the ball launched off the spring vertically. We won't do that. We're going to leave that alone until we talk about oscillations. And you guys should have springs down by the time we get to oscillations, by the time we get done with oscillations. So no springs and no two-dimensional collisions. All right.
Professor Boyd, should we know how to find the I value of a like curved two-dimensional object? Because we do just like you give us like just the bar, put at different positions along the x-axis, but are you ever gonna like curve that and make us find I?
No, we'll talk about that today. One of the problems I want to talk through today has you find the total moment of inertia of the bar with two blocks on it. And when you see that, you'll understand how we do it. I won't have you do anything crazy like a sphere on a rod that you have to do the parallel axis to figure out.
Okay, so
At worst, it'll be what you're going to see today in this example from this test. Well, I think it's the second test, actually. Any other questions? And by the way, this is essentially what your equation sheet will look like. This has everything on it that I can think of. I might take stuff off here, but it's got everything. Like, we don't need the angular momentum. We're going to do that after the exam. But yeah, it should have everything on there. So if there's no more questions, I want to talk through the solution to this problem, if that's okay with everybody. So in this problem, and I'm going to kill my video. In this problem, what we have is we have two pulleys, and the two pulleys are connected by ropes. One of the pulleys is actually two pulleys welded together, and there's a mass hooked onto each one. If you read through the problem, you find out that we don't know this mass right here, but we know that it's falling and we know this one's rising. And so we're going to go through the steps of how to solve this. Like normal, we would have relevant concepts and equations. I just want you to list some of the things that you know you'll need. If you're doing this with torque and forces, you need free body diagrams, you need torque diagrams. You need to understand that A is equal to R alpha, things like that. Moment of inertia of a pulley, all those type of things. Then it says to draw a free body diagram and a torque diagram for each one. And so we'll talk through what that is and what I want from you. So when you draw a free body diagram for each of the masses the same way we've always done. And we have mass 1 and mass 2. What I do is I just draw 1 and I draw 2. I know there's a tension up that I'll call tension 1, and I know that there's a tension up that I'll call tension 2. There's always a weight, M2G, M1G. And then these have different accelerations. I'm going to say it's down. Now, one thing I don't want you to do is this problem says it has constant velocity. Don't automatically set this to 0. Solve it symbolically first and then come back to it. Now, we have two pulleys here, and we're going to need to do torque diagrams on each one. And a torque diagram is similar to a free body diagram in that what you do is you draw the axis of rotation, so this is for number 1, we see that at R1, we have some tension that goes to the second pulleys. I'm just going to call this TP. That is this line right here, and it's at a distance R at the radius. I'm going to call this R1, and I'm going to say this is tension 1. From my free body diagram, there's a tension pulling this mass up, there's a tension pulling this pulley down. For the 2-3 pulley, you have to be a little bit more careful because these are at different R's. So at R2, and I'm calling it R2 because it's the distance for the pulley 2, I have TP again. And by Newton's third law, we know that these are equal and opposite tensions, so they are the same tension. And then here I have R3, and I have tension 2. And I'm going to stop for a minute here and make sure everyone understands what we've done so far. Because if you can do this, you're good. If you can do this, you should be fine for everything else that happens. Now we see that both of these pulleys are rotating counterclockwise, and counterclockwise rotation is positive rotation. So they both have positive alpha. And I need to make sure, and I write that somewhere, because just like on the torque diagrams where we write A, we need to write alpha. Secondly, I need to see if these torques are positive or negative. I can do that by just, you don't have to draw these, but this is what we're doing. R1, T1, I'm turning that to T1. So I know that this is positive because it's a clockwise rotation. Similarly, this R is going to turn counterclockwise. This one's negative. Positive, negative, right? You can see which way that torque is going to cause. This force is going to make this pulley rotate this way. This force is going to make it rotate this way. And you need to just list those. The reason for that is that when we get to the next question, writing Newton's equations, we need to be able to just use our diagram to write down the equations. There's one small wrinkle here, and that's that, well, let's do these two first. And I'm going to write them right here just so that we can see them. Hi, Mohammed. We're recording, but just so you can see them, all you have to do is write M1A1 is equal to M1G minus T1. And here, M2A2 is equal to oh shoot, I'm sorry. I flipped that the wrong way. Is equal to T2 minus M2G. You might want to, at this point, also just solve these for T1 and T2. That would be M1G plus, nope, minus M1A1. And this would be T2 is equal to M2A2 plus M2G, okay? That we've done a million times, so I'm sure you're okay with that. These ones, the wrinkle comes in where this pulley, if we look at it, is actually two pulleys connected. They're welded together so they will move with the same angular acceleration, same alpha. But I, for this, is just M1, well, I should call this M pulley 1, R1 squared over 2. I for 2 and 3 is the combination of them. It's M pulley 2, R2 squared over 2 plus M pulley 3, R3 squared over 2. Okay, make sure you understand that. That's because these are welded together. And you need to find those. And we'll talk about that in a second. But once we do that, we can look at these torque diagrams and write down what I1 or I pulley 1 alpha is. And the alphas will be the same because they're connected by this rope. If this one turns, This one turns, same amount. So IP1 alpha, remember, was positive R1 T1 minus R1 TP. So all we're looking at is we have positive alpha, positive R1 times T1, negative R1 TP. These are 90 degrees off because they're pulleys. The beautiful thing about a pulley and a tension on a pulley is it's always 90 degrees off. So the torque would normally be R cross F or RF sine theta, where theta is the angle between them. But the angle between them is always 90 degrees, which is great. So for this guy, we have R2TP minus R3T2. And remember, this is pulleys 2 and 3. Alpha is, what was it, R2TP minus R3T2. And now that we have these, the whole system, right, we could essentially solve this for alpha, but really what you can do is you can add these two equations together. We also should note that R2 is equal to R1 here. And we can add these, just add these two equations, and what do you get? You get IP1 plus IP23 times alpha, because the alphas are the same since they're connected at the edge. And I'll leave that the same. If I look at this, I get RT1 minus R1TP plus R2TP minus R3T2. But, and you should already know this from Newton's third law, that internal forces cancel, right? R1 and R2 are the same. These two forces go away, or these two torques go away. Internal torques do the same thing. So I'm just going to call this I total. Alpha is R1 T1 minus R3 T3. And when I look back to this, I'm sorry, that's not T3, that's T2. T2. When I look back to this, I've already solved for T1 and T2, and I'm going to put those in. I'm going to put it all together. So let's put it all together. I total alpha is equal to R1 T1 minus R3 T2. And just plugging these in, I get R1 is M1G and A minus A minus R3 M2 plus okay, so here's the next hard part of this that you need to make sure you understand. And this problem illustrates it really well. We know that on the edge, the further out that we go, if this whole pulley is rotating with alpha, we get different values of A. So A is our alpha, okay? These pulleys have the same alpha, but these A's are different because they're at different radiuses. So A1 is really R1 alpha, and A2 is equal to R2 alpha. Now, if we want to get everything in terms of alpha, which is what we want to do because that's what they're all, plug these in for those. So we get, and I'm going to move them over as well. I total, this becomes M1 R1 alpha with an R1 on the outside. So this is plus M1 R1 squared. This is minus M2 R3. Sorry, this was R3. R3 squared alpha. So this is M2 R3 squared all times alpha. All I did was I substituted these in, and then I moved those terms over. And that's equal to M1G R1 minus M2G R3. And now let's look at this equation and what this equation is actually telling us. It's telling us the net torque. Remember that torque is I alpha. The net torque here is equal to the sum of the external torques. The external torque on this system is gravity pulling this mass down at a distance r, and gravity pulling this mass down at a distance r. This one's positive because it's rotating positively. This torque is causing a positive rotation. Once you've done that, you can see here that we know I total, if we go back, remember was P1 and P2. So we know the mass of the pulley. We know R. We can find this. We can find this. We can find this. Remember that those are centimeters. So that's 7 millimeters, 4 millimeters. These things are tiny. You're going to find that mostly they don't contribute a whole lot. We know mass 2 is 3.5 kilograms. We know R3 is the same radius as this pulley 3, and R1 is 0.7. So when you plug all that stuff in here, you can solve this for mass 1 because you know everything else. It's a little hard, but we're going to show you how this becomes easy. The reason why this becomes easy is we know that it's rotating with constant velocity. And it asks here, what is the linear acceleration? What is it? What is the angular acceleration? How do you know? This is kind of a trick, you guys. If we go back up, we're told it's moving with constant angular velocity and constant linear velocity, which tells you that all of these are 0. And so when we go to here, you probably don't, you might have been able to do it a little earlier, but I would prefer you not to. I get that I alpha, all that I stuff is 0, is M1G R1 minus M2G R3. And we can see that M1G R1 is equal to M2G R3, canceling the G's. M2 is equal to M1 R1 over R3, which is really easy to do because we know that M1 is 3.5, R1 and R3 were 7.7 and 0.4. So plugging that into my calculator, I would get 0.7 divided by 0.4 times 3.5. I get 6.125 kilograms. And that's it. That's this whole problem. So to go back through this and talk about this, the first thing I need you to be able to do is draw the free body diagrams and then draw the torque diagrams. And you can see that for the torque diagrams, everywhere that you have a rope on these pulleys, you better have a force. And you better be able to say what that force is. And you better know the difference between the, you know, that this is the same tension, this is a totally different tension, and this is a third different tension. On the torque diagram, you need to choose which way you think it's going to be rotating. You're usually given that, but that tells you if alpha is going to be positive or negative, because remember, we're trying to find this equation right here. And we need to figure out what is alpha, what are the torques, what is I. If the pulleys are stuck together, you treat them as one big pulley with the moment of inertia of both pulleys. And then the last little wrinkle is when you put it all together, you have to figure out how A and alpha are related. And they may be the same. If this mass was on the outside, A and A would be exactly the same because their alphas are the same and their R's are the same. So if you can do all that, the rest of it is what we did way back in chapter 5 and 6 of just plugging other equations into equations and solving. Is there any questions on this particular problem? If you
For
go
the
back,
test, you're
what's
gonna
that?
give. I'll say for the test, you're gonna give us a similar one. How, like, what other ways could
You
you
could
like
have one of those blocks could be on an incline.
Okay.
And if it was on an incline, I think there is a problem like that somewhere. we can do that right now, just at least part of it. Let me set up a problem like that. I think I did it in lecture actually. So imagine you have a block and you have a pulley and you have another block. And you could have friction here or maybe not. Let's say we do have friction. This is mass 1, this is mass 2, and this is our mass P. Let's say we have friction and this thing's moving that way. So this is rotating backwards and this is dropping. Our free body diagrams for, I'll do 2 first. And I'm going to say that they're both connected on the outside of this pulley has a radius and a mass. So for mass 2, we would have a tension 2 and we'd have an M2G and it would have an A2 down. This guy, you have to go back to what we did in 5 and 6. Normal weight in the Y is mg cos theta. It would have tension going up, which we'll call tension 1. It's going to have going down weight x, and remember that weight x is mg sine. And then the last thing you have is you have your force of friction, which remember your force of friction is mu n, which is mu mg cos from the y equation there. So our free body diagram here gives us the equations if we assume that A is that way. There's no A in the y. This is A1. Gives us M1 A1 is equal to T1 minus M1G sine theta minus mu mg cos theta. For M2, M2 A2 is equal to M2G minus T2. We know that A is related to alpha by AR alpha. Now let's do the torque diagram on this. So we have a pulley rotating here. At R and at R, we have tension 1 and we have tension 2. And this pulley is going to rotate clockwise. That alpha is actually negative. It's clockwise, right? I for this thing is mr squared over 2, where's the mass of the pulley. We write I times negative alpha is these two torques. Doing the torque diagram, I can just say R T1, and that is a positive. It's trying to rotate it positively. R T2, and this is negative. If I try to turn R to T, I'm rotating clockwise. That's negative. So this is R T1 minus R T2. Going back and solving these for T2 and T1, I can see that T2 is going to be M2G minus M2A. That doesn't look right. Did I do something wrong here?
You need to swap. I think it's I. If you already put the negative alpha, wouldn't it be
Oh, no, yeah,
RT2?
you're right. No, you're absolutely right. It's fine. I forgot about the negative alpha. So this is, okay. For T1, I'm going to move those two terms over. So T1 is going to be M1 A1 A2 plus M1G sine theta plus mu M1G cos theta. If I put those in here with the negative sign, I'm going to move the negative sign through. So what I get is RT2 minus RT1, and I alpha is RT1 minus R, sorry. My brain is not always the happiest thing in the morning. RT2 minus RT1. I'm plugging these in. I'm just going to put R. T2 is M2G minus M2A2. Remember that A2 is R alpha, so M2G minus M2 R alpha plus R times R minus R times all this stuff. M1, A is R alpha, M1G sine theta plus mu M1G cos theta. And then you can see that these are all negative now. Move the alphas over and I get I plus M2R squared plus M1 R squared times alpha is equal to R times M2G minus R times M1G sine theta minus mu M1G cos theta. So these two things are, oh, there's an R here, sorry. So these three things, if you really look at our beginning problem, the torque on the whole system, as it rotates that way, it's caused by this torque due to M2G. This force is causing this thing to torque in the negative direction. It's being slowed down by the torque due to the weight down the incline and the friction of mass one. And that's what we're seeing here. This is the net torque acting on the system. It's equal to the torque due to the force M2G minus the torque due to the force of the weight of M1 down the incline and the friction. And that's all that's happening in these problems. They're a pain to set up because the torque diagram makes it a pain. But then, unlike the other one, this doesn't have to be constant. This could be some number. And let's say I gave you M1, M1, M2, and R, right? I don't know who that is. Whoever's mic's on. No one's mic's on? Oh, I'm sorry. That's actually my dishwasher. Anyway, I thought that was someone's mic and someone was going to the bathroom. I'm so sorry. That was weird. Anyway, my dishwasher's on and I'm right on the other wall of it. So if you hear water running, that's actually my dishwasher. I promise. I'm sitting right here.
I have a quick question before you move on.
Yeah.
So we're doing the I on the left side right here. It's the I total, so it's I plus M2R squared.
Mm-hmm.
So the M2R squared, that's the I value for the pulley.
So this I value for the pulley is the mass of the pulley times the radius of the pulley squared over 2. That's for any wheel.
Yeah.
So if I gave you, it was let's say I said this guy was 5 kilograms and this was 10 kilograms, and this had a mass of 1 kilogram and a radius of 0.5 meter, right? You could find the I of this would be 1 times 1/2 squared over 1/2, or 1/8 is what that would be. These look a lot like point masses, right? Basically what we've done is we're treating this system like it was a rotating wheel connected to a point mass connected to it at some radius and another point mass connected to it, and it's trying to rotate. Which is really weird that you can see it as that, but you could look at this as like a scaffold problem where this has a force and this has a force, and it's trying to make the whole thing rotate. And these are point masses.
Yeah.
That's exactly what this looks like.
Yeah.
2 point masses, this is something that's got some volume. So it's an extended object, in this case, the pulley, that has a moment of inertia due to the fact that there's a mass distribution around the axis. Whereas we're treating the other two as point masses. And then this side is just all the forces times wherever they're being applied to the system. It's kind of neat that you can totally see that. But what I was going to say is if alpha was if I asked you to solve for alpha, so I gave you the angle and I gave you M1 and M2 and I gave you the pulley moment of inertia, you could find alpha. And then once you find alpha, you know that A for both of these is equal to R alpha. And so you could, well, you could tell me how fast they're falling, like the amount of time it takes, or what their final velocity was, all from those, if we start them from rest, from these V final squared minus V initial squared is equal to 2A Y final or X final. From those equations, right, that we had. We could also find V is equal to R omega. So if we found V final, let's say alpha ended up being 1 rad per second squared, and R was 1/2, we said, then A would be 1/2, right? 1/2 times 1. Plugging that in, we could find, if it started from rest, we could find after it dropped 4 meters or something, we could find V final. Once we found V final, by plugging this in, we could find omega. And omega is V over R, and that would tell us how fast the pulley's rotating when the masses are moving with that velocity. They're all connected by frictionless, massless, stretchless ropes. So we know that those things are related. The only caution I have for you is, like in this test question here, because this is at a different radius, he has a different acceleration, A. They have the same alpha. These pulleys have the same omega. Therefore, V and V are different, because there again, V is equal to R omega and A is equal to R alpha. Because they're at different radiuses, they have different V's, they have different A's. These have the same alpha and the same omega because they're connected by a rope at the same radius. If they were connected, like if say this rope went to the center pulley, this alpha would be different from this alpha. And that's because this rope would have to go 2 pi r around once. And when it did that, this one would spin much greater. So it could end up being like double or triple. I won't do that to you. I'll make sure that the pulleys are connected so the pulleys will have the same alpha, but you may have masses at different radiuses. So just make sure you're really clear on that. Okay. I think that's all I have on those type of problems. If you go back and look at Thursday, we talked about how to do this same problem with energy. So you could do all this torque diagram stuff, or you could do energy. But I'll tell you this, that the energy, if it's moving with constant velocity, the energy doesn't make any sense because the energy is going to be the same. I guess it does make sense, but essentially, if it starts from rest and falls, do energy. If it's moving with constant acceleration, do torques. Because as you see in this solution right here, doing the torques gets you to the answer really quickly if A and alpha are 0, right? Which is nice. So I don't know, it's really up to you. And what you'll probably have is you'll probably have a problem that you can choose either way to do it. I don't like doing that because it makes it harder for me to grade, but I like giving you the choice. If you're more comfortable with just writing down the energy, then you can do that. And in the real world, that's what you're going to do when you have to solve these types of problems that may not look like blocks and pulleys, but really are blocks and pulleys. If you think about it, they're modeled the same way. They're just different objects, right? So if we're cool with that, I'm going to move on to the second type of problem. And this is really in homework 7, which I put up a video solution to. This is really the most important type of equilibrium problem. We have 2 different types of equilibrium, and we've talked about this already a bunch, but I'm going to talk about it again. Equilibrium means nothing is moving. Nothing is moving at all. So if nothing is moving, the forces all have to equal 0, and the torques all have to equal 0. And the forces can equal 0 in the x or in the y, okay? So with these types of, I call these scaffold problems, because they're like a scaffold that you would see hanging from a building. They usually have a wire on each end, and you have to figure out if it's in equilibrium, what maybe the mass 2 is, or what the wire tension is, or whatever. And we'll go through how to solve this really fast. So in this problem, the actual problem takes you through how to solve these. We know what M1 is. We know it's 5 kilograms. We know the bar mass. What we don't know is we don't know this wire that's holding on to keep it from rotating. We don't know the tension in that wire, and we don't know M2. But we know this thing is trying to rotate counterclock or clockwise. And this wire that's holding it is keeping that from happening. So M2 is going to be greater than M1. It's got to be. And whatever the difference in those two torques is, this guy's going to be supplying it, right? So together, the torque from the weight of this and the torque from the tension of the wire are keeping the bar from rotating clockwise. Again, sorry, that's my dishwasher going. If you're hearing water jumping around in the background. So if you go through relevant concepts, these are the relevant concepts. Torque is RF, sine of the angle. I don't know what else. So let's draw a free body diagram showing all the forces on the bar. And here you don't pick an axis, you just write the forces. So at the center, we're always going to have a weight. This is mass of the bar times g. At the edge here, we're going to have M2g. At this block, M1g. And here, we're going to have a tension in the wire. The last thing you have to have is a normal force. You know that because these have to be in equilibrium, and we wrote 4 forces, all in the negative y. There better be a force in the positive y to counter all those. And we're actually told that that is 1800. So that is our free body diagram. That's what our free body diagram looks like. We don't have to draw one for each mass. We draw one for the whole system, and we just write the forces that we know are there. You have to know there's a normal force. It tells you. You have to know there's a tension in the wire. It tells you. And you have to know that there's weights. Where you might mess up is forgetting that the bar has a weight itself. Every mass has a weight. Every wire has a tension. There's always a normal force on the if it's sitting on something, okay? Now from that, it says draw the torque diagram acting on the beam. In equilibrium, you can choose anywhere on this beam. We could put it anywhere we want. But I tell you, put it at the center of the beam. The reason why we're putting it here is then we won't have to consider the torque due to the weight of the bar or the torque due to the normal force. If it was here, we would have to consider these 4 forces. By choosing it at the center, we only have to deal with these 3. Let's look at that torque diagram. The access point is here. I'm going to rotate back up for a minute. At R, which is the 4.5, we have the tension of the rope. And at 6 meters, which R is 6 meters, we have M1G. And then on this side, we have R is 6 meters, and we have M2G. We don't consider the normal or the weight of the bar because they're on the axis, which means that their R is 0. Or another way to see it is they're, in effect, parallel to the axis, so they don't cause a rotation. You can't rotate something by pushing on the axis, right? You have to push perpendicular to the axis at some radius to cause a torque. Again, looking at these torques, R and F, these are both positive. This guy's negative. Normally on a torque diagram, you would draw alpha. Alpha doesn't matter here. It's in equilibrium. It's not going to rotate. So knowing that, we write that 0 is 6 times m1g plus 4.5 times t minus 6 times m2g. Are you guys cool with that? If you can get that torque diagram down, I think the force diagrams are easy, but this torque diagram is a little bit harder. Here, the sum of the forces in the y has to be 0. We see that n is positive and everything else is negative. Now, in this equation, I don't know m2. I don't know the tension. So I have two unknowns here. And in this equation, I don't know t and I don't know m2. So let's write those down at the bottom. N is equal to, if I move everything over, m1g plus t plus m2g plus, was that it? Yeah, that was it, sorry.
For these equilibrium problems, how do you know like which way it's accelerating to know which one is positive?
There is no acceleration. It doesn't matter whether you call them positive or negative. They just have to be opposite of each other, to be honest. Because they're in equilibrium, you're going to get a 0 for the acceleration. I generally just imagine that it's going to rotate positively, and I write those down. Here, for the torque equation, I'm going to move, you'll see why. I'm going to move this guy over. So I get, in fact, what I'm going to do is I'm going to write 6 m1g minus, no, let's not do that. I'm going to write 6 m2g is 6 m1g plus 4.5 t. And now here, what you see, we know n is 1800. We know m1 is 5. We know g. And again, you can use 10 for g. And I'm going to do that in a second. I don't know this, and I don't know this. Here, I don't know this, and I don't know this, but I know that this is 5. So, using 10 for g, I have 60 times m2 is 6 times 5 is 30, times 10 is 300, plus 4.5 t. If I divide by 60, I get m2 this is 5 dividing by 60. How many times does 4.5 go into t? Go into 60. This is 0.075 t.
Professor,
Yes.
I had a question. So if we're considering the normal force, shouldn't we also consider the force of the bar, like the m bar g?
Did I forget that? No, that's right here.
Oh, I didn't see the, okay.
Did I drop it though? You know what? I think I dropped it here. Yeah, I totally dropped it here. I'm so sorry.
Okay.
I felt like something was wrong. The bar is 100 kilograms. So what we get from this equation is we get 1800. Let's move this over. So 100 times 10 is 1,000 is equal to 5. Nope, let's move that one over too. So this is 1800. This is 50. This is 1,000. This is t, and this is 10 times m2. Minus 50 is equal to t plus 10 m2. This would be 750 is equal to t plus 10 m2. And then you've got a few choices of how you can solve this. One thing you could do, let's solve this for m2. M2 would be 750 minus t all over 10. So I have M2 is 5 plus 0.075 t. And here M2 is 750 divided by 10. So 75 minus 0.1 t. I can subtract these two equations if I want. Or I could, Yeah, let's subtract them. So M2 minus M2 is 0. 5, this is minus 70. This is minus a minus, so this is plus 0.175 t. And I see here that 0.175 t is equal to 70, or t is equal to 70 divided by 0.175. 70 divided by 0.175 is 400. So I know my tension is 400 newtons. If I want, I can just plug it in here to get M2. 400 times a tenth is 40. So M2 has to be 35 kilograms. That's the whole point of this. You set the forces equal to 0 in the X, in the Y. We didn't have any X forces. We set the torques equal to 0. And that gives us two equations that we can use to solve for the two unknowns. And at that point, you could do it by substitution. You could substitute for M2, 75 minus 0.1 t here, and then solve this whole equation for t. You could add or subtract them. I don't really care what you do. But the point is, you have to use the two of them to solve for your two unknowns. I'm sure you've done that in algebra or calculus at some point. But that's the point of this, is we set the forces equal to 0, we set the torques equal to 0, and we use them to get our two unknowns. If we had three unknowns, we would be done. We can't solve for three unknowns with only two equations. We would have to find a third equation. Sometimes you can do that though by using the axis. Now, check this out. We didn't know M2. If we had put the axis right here, our torque equation, right, would have given us M1G at 1.5. And then we would have had at 4.5, we would have had the normal force. And at 4.5, we would have had M bar of G. And then at 10.5, we would have had M2G. And you could have solved this. This would be a positive torque. This would be a negative. This would be a positive. This would be a negative. You could say 0 is 1.5 M1G plus 4.5 N minus 4.5 M bar G minus 10.5 M2G. And here you only have one unknown. So you totally could have done that and solved it for M2 there. And then gone back and used maybe this equation to solve for the tension. It doesn't matter how you do it. You're going to get the right answer, as long as I don't mess up. These problems are a little hard to write because I have to make sure that they are in equilibrium. Here's a really quick test your comprehension. If I had a bar held by one wire, okay, can this be in equilibrium? And the answer is no. And why is it no? The answer is no, because if this is some r away from the axis of rotation, if I put the axis of rotation here for my torque equation, I would get that 0 is equal to RT. That is not 0. And if I put it here, I would get that 0 is equal to RMG. That is also not 0. So in order to have these equations actually work, I have to be careful that I don't do something where you could set it at some axis and it would rotate. And that's always a danger. I try to do them the right way. And if that happens on an exam where you find somewhere where it's not giving you 0, let me know, because I've probably done something stupid. But otherwise, so this problem asked for you to draw the torques, write the equations, and then find the tension and the mass. We just did that. Now this problem is going to flip into what's called an elasticity problem. And those elasticity problems were the end of chapter 12. And they basically say that if you have some force acting over some area, you get this constant called Young's modulus. Sometimes this is a Y, sometimes it's a B, sometimes it's whatever. Engineering, physics, all use different letters for that. But essentially what this is pressure. This is known as the cross-sectional area. And for a wire, if I try to pull on a wire, try to pull a wire apart with some force, this A has to be pi r squared. So as I'm pulling on it, it causes a length change. And however long this wire is, the length change, due to me pulling on it, some delta L, is L times the force that I'm using divided by E times A. And E is this modulus that tells you how hard it is to actually pull the thing apart. There's also something called ultimate strength, and that's in the homework. Just know that at ultimate strength, delta L is equal to L. So delta L over L gives you 1. And the force for ultimate strength when the thing's going to break is sometimes given as EA. I don't agree with that, but that's what your book does in that particular problem. It's like the second to last problem in that homework. But anyway, so we have this, and we're told to find out that the steel wire will break if it's stretched more than 1 micron, if delta L is greater than 1 times 10 to the minus 6. So we need to find whether or not we're going to break this wire if we apply a force of 40 newtons. Okay, so what we do is here, we're given the length is 3 meters long. We're told it's steel, so L is 3. Our tension force is 400. E is 2 times 10 to the 11th, or 20 times 10 to the 10th. So this is 2 times 10 to the 11th. And finally, our cross-sectional area, I just gave it to you. You didn't have to use this pi r squared, is 5 times 10 to the negative 3. You can do this almost in your head. This is 10 times 10 to the 8th. So this is 10 to the 9th in the bottom. This is 12, or 1.2 times 10 to the 3rd. If I take scientific numbers and if they're divided, you subtract the bottom one. So this is 1.2 times 10 to the 3rd minus 9. That's 1.2 microns. And you can see that that means that delta L is greater than 1 times 10 to the minus 6. And the wire breaks. That's all you have to do here. These are plug and chug. You have to set them up for whatever I'm asking you for. But if I want the force, and I give you the cross-sectional area, and I give you E, or I tell you to look up E in your book, I give you delta L and L, you could find the force. If I gave you F and A and delta L, you could find the length, blah, blah, blah. Those aren't particularly interesting. But what you can do with them is you can find out things like, does a wire break due to the tension that you found earlier in the problem? Now, if this wire breaks here, we remove it from our equations. We've already done the hard work. Remove this. And what happens? Well, we haven't done all the hard work. If this is removed, then obviously M2 is going to cause this whole thing to rotate. And what we need to do now is do a new torque diagram, which we already know. R and R, M1, G, M2G. Take it about the center axis because this thing's going to rotate about that pivot point. And we know this is a positive, this is a negative. So we have I alpha is M1GR minus M2GR. And I ask you for alpha. But that means you're going to have to find I. Now, I for the whole system has to be I of mass 1 plus I of mass 2 plus I of the bar. I of mass 1 is just mr squared, m1r squared. M2R squared. It doesn't matter if they're negative or positive, you're just going to square them anyway. So these are both 6. And we know M1 and M2 now. So M1 we said was what, 5, and M2 was 35. And then the bar is MR squared, nope, ML squared. It's a bar about its center, and about its center, it's over 12. So this would be, M of the bar was 100. The length is 12. It's 6 plus 6 over 12, or 112 cancels, and I get 1200. So I get 1200 plus 5, and so basically what I would get is 5 times 6 squared plus 35 times 6 squared plus 1200. And this ends up being 40 times 36, so 40 times 36 is 1440 plus 1200. This ends up being 1640 kilogram meter squared. That is our I, okay? So really alpha is M1GR minus M2GR over 1640. M1 times G is 50. M2 times G is 350. So this is 50 times 10, I'm sorry, times 6 minus 350 times 6, or 300 times 6 is 1800 over 1640, but it's got a negative sign. And that's 1800 divided by 1640 is 1.09, so 1.1. It's negative, why? Because it's rotating clockwise. So you know it's negative, it has to be negative. That just tells you that it's rotating clockwise in our setup. And that was all I asked. Once you find it, it tells you though, notice, it tells you that I for the beam at the center is ML squared over 12. And to treat each of the masses as MR squared. So you just need to know to add them all together and to figure out what L and R are, really. And once you do that, as long as you know how to write a torque diagram, it's pretty fast to calculate. If you don't, you're going to be just lost and floundering around, right? The rest of this test, we did that on Thursday. You can ignore this problem because this problem is about angular momentum, and we're going to cover that later this week or next week. It makes more sense to cover it when we do gravity. So let me go to the other module. And there's really only, I'm not going to talk about the first problem because we've already done that to death and I don't want to waste your time anymore. But I want to talk about the second type of equilibrium problem. That wasn't what I wanted. That's the solution. I don't want the solution. Right here. Okay. So for this first problem, you should know, sorry, that was what we just did, wasn't it? I'm so sorry, you guys. I'm wasting your time. So for this first problem, the only weird thing about this, so do these torques and note that the acceleration of this is going to be different than the accelerations of the outside. These two pulleys have different alphas, but because it's a negative, you can go through and just look at the solution to this. It's not too bad. The only weird thing is that it looks weird, and it's actually super easy if you treat it as a double pulley and this was just a mass hanging here and a double mass. You'll see that if you look through that solution. But it's exactly what we already did. But this is what I want to talk about here. So this is the other type of equilibrium problem, when it's not a scaffold. This is an equilibrium problem where things are all at angles. And there's some really important stuff to talk about here. So this problem's in your book. It was like a firefighter on a ladder or something. There's a problem in the homework with a guy leaning on a wall that's like a runner. He's like in running gear. But they're all done the exact same mechanical way. And how that is that you have to assume that the wall, the vertical wall, is frictionless. I mean, I guess you don't have to. And the floor has friction. And the reason why it has to, we'll see right now. But imagine a beam that goes here. And on this beam itself has a weight. And we're told that that weight is at the half. So if this whole thing has an L, going from here to here is L. Then from here to here is L to the half. And that's right where the weight of this thing is. And then we're told that there's two other weights. There's a guy standing here at some distance and a guy, or a toolbox here. Now, when we draw the forces, and this is the one part that actually gets a little tough, and I'm going to do it with the red pen. It's touching the ground, so it has to have a normal in the Y. It's touching the wall, so it has to have a normal in the X. It has friction to keep it from going that way. So that friction here, and that friction will be mu n of Y, the normal force where the friction is being applied. That you have to know. It has a weight that's at L to the half. This is the weight of the whole ladder. And then it has a weight of a man that it gives you. And it has a weight of a toolbox. So I'm just going to call these weight T, weight L, weight M. So the forces in the X are simply Nx minus mu Ny is equal to 0. And you can see that this, if we want to solve for mu, move that over, is Nx over Ny. And that's usually in these problems what we're trying to find. We're trying to find the coefficient of friction that keeps this thing from falling. And I believe that's what we're finding in this problem. The forces in the Y are, we have an Ny up minus a weight of the toolbox, minus the weight of the ladder, minus the weight of the man. And that's it. This, of course, equals 0, right? And so we can see that Ny will equal the weight, these are all the weight of the toolbox plus the weight of the ladder plus the weight of the man. That's easy enough to find. We can find that right away because we're given all of that stuff right here. We're told that the mass of the man is 30, the ladder is 25, and the mass of the toolbox is 5. So 5 plus 25 is 30. This is 60 times G. These are all mg's. So this is 60 times G. This is 600 newtons. We know what Ny is. Now, how do we get Nx? In order to get Nx, what we have to do is torques. We have to do the torque as if the torque here were 0. Anywhere but here, really. But I'm going to do it here because these are all easy to find the torques to. So if I do that, I know that I have a weight of the, I'm going to start with the man, and that he's at a length of 2/5 L. That I could do some weird, fun angle and try to figure out that this is my R and this is my force, where it's M of the man times G. But I don't need to do that because I know this angle. And so what I really want is I know that for this R vector that's equal to 2/5, I have an Rx and I have an Ry, right? And Rx is 2/5 L cos 30, and Ry is 2/5 L sine 30, right? So which one do I want? Which one of these gives me a torque? Well, this force is in the negative Y. If I multiply that by the positive Y, that's not a torque. However, Rx is perpendicular, so the torque due to this man is Rx times the weight of the man. Or in our force diagram, Rx weight of man. And it's a positive torque, right? So this would be 2 fists L cos 30 times mass of the man times G, which is exactly what this is, right? So when I do that for each one of these, for each of the weights, I need to find R to the man times the weight of the man. I need to find R of the ladder to the weight of the ladder. I need to find R of the toolbox to the weight of the toolbox. And each of these, RM, RL, and R toolbox, the man is at 2 fists, L cos theta. This is at 1/2 L cos theta, and this is at 2/3 L cos theta. The last thing I have is I have this normal in the X. And this is where things get a little different because here my R is L, the total length, but my force is this way, my normal of the X. So I need to find either R Y or R X. And you can automatically see right here, RX and NX are opposite each other, so it's not going to be that R. Find this R. And you know this R is L sine theta. So this last torque is really R, or I guess I should say L sine theta. No, don't do that. I realized I was putting it in the wrong direction. L sine theta NX. And this whole thing is in equilibrium, so it's not actually going to move. But I know that these R's are all, or these torques are all positive and this one's negative, right? So I have that 0 is RT, weight of T, plus R man, weight of man, plus R ladder, weight of ladder, minus L sine theta and X. Move this over and I get NX is RT, weight T, plus R man, weight man, plus R ladder, weight ladder, all over L sine theta. That's easy to do, right? Because you know the mass of the toolbox. You know that this is mg for each one. So 5 times that. You can find each of these. This is the important part. It's figuring out what your lever arms, what your radial distances that cause the torques are. Once you have that and you find NX, you're just going to plug it in here. So you found NY using the force in the Y. You found NX from the torque equation. And once you have them both, you can set them as a ratio and get your coefficient of friction. This latter problem is actually done in your book. It's done all over the place online. Just make sure you understand it. The hard part is really understanding where these lever arms are, that you want Rx. You don't want to do this. I'm going to call this R and I'm going to figure out the angle between them. If this is 30, then this is, 60, and I have R here and weight here. And so I know that this is, if this is 60, then this is, and doing all that stuff. Don't do that stuff. Just figure out the perpendicular radial direction and solve for the torques. That's really all there is to this. Okay. The last thing that it says is it asks you, it asks you if the static friction were actually 0.9, what is the smallest angle the ladder could be placed at against the wall, and how would you find this? Okay, well, if we go back to this torque equation, we see that we could solve this for sine theta, right? In fact, what we would have is each of these would have a cosine. So really this whole thing would end up being something nx times something, right, times cos over sine, so 1 over tangent. And so you could actually, if you plug this stuff in, each of these terms has a cosine. So cos over sine becomes 1 over tangent. And this really becomes tangent of some stuff over an x. And take the arctan and you can find the angle. Assuming that assuming that nx is 0.9 times ny, and you found ny, right? So there's a little bit of work that you'd have to do there. You'd have to find what nx was, and then plug it back into that equation and solve for the angle. It's a little hard, but it's not too horrible. So that's it. The only other thing that I wanted to talk about was, just as a refresher, ballistic pendulum. If you have a block and you have a bullet, and the bullet initially has some velocity and the block doesn't, and then they collide inelastically, okay? So they collide inelastically where afterwards they are stuck together and they have some initial velocity. You do inelastic collisions just with momentum. M of the bullet, V of the bullet initial, plus M of the block, times V of the block initial is equal to M plus M, little bullet plus block, times V, final. Find V final. This is 0 because the block's not moving, right? So V final is quite simply, I'm just going to call this M1 and call this M2. Is M1 over M1 plus M2 V initial, okay? Once you have that, turn this into a energy problem where you have an object that has some potential energy and some kinetic energy, and that object can swing up to some height, h, where h is equal to, now h here, if this whole thing is L and this is L, then this distance is L cos theta. So h is equal to L minus L cos theta. So whatever h it gets up to, it only has potential energy of mgh up here. So this is mg y initial plus mv final that you just found. And remember that m is actually m1 plus m2 in this part. And up here, h is L minus L cos theta. You say that this is 0, this is your h, and you get that mgh is equal to mv final squared over 2. The m's cancel. H is equal to v final squared over 2g. All good. That's a ballistic pendulum. Make sure that you know, well, that you understand for yourself that concept, that we can start off with a collision and then use energy to get our answer. Or for the skier problems and a few other problems, that we can start off with energy and turn it into a projectile motion problem and ask, how far does it go or something? How high does it go? There's a skier problem in the homework that does that. Going back to the beginning of this lecture, as I said, we're going to have energy. We're going to have 5 problems on this exam. One will be energy or torque, or energy and torque, or torque, which is just blocks and pulleys. You could have an inclined plane. Then you're going to have a problem that you're just going to need to do with energy, like the truck from Thursday, where it goes down a hill and comes up another hill and stops. We've done a bunch of those problems in homework. You just set the energies at A, B, C, D, whatever, equal. You may need to know what to do with friction, where to put it. You should know how to do that. Collisions are super easy. All it is remember that on collisions, there's those equations, but for elastic, they bounce. And the kinetic energy is, the change of kinetic energy is 0. Inelastic, they stick together, and the change in kinetic energy does not equal 0. Whatever is lost, it's always going to be negative. Whatever is lost is energy lost because the two masses stick. They don't have to be these billiard balls, you know, moving. They could be 2 cars. They could be a truck. They could be a bird grabbing a fish out of a lake, all sorts of things that you can do with these. But essentially just think of them as two masses that come together in a collision, and initially the second mass is at rest somehow, okay? The equilibrium problem here with possible elasticity, those are the two that I went over today. The scaffold type problem with the two masses in the wire, or the ladder type problem. And then there may be a ballistic pendulum type problem where you have some energy and you turn it into a collision or a projectile motion or something. Other than that, really just make sure you go through the homework solutions that I gave, so that if you're having trouble understanding torque, hopefully they'll help you. Homework 6 is really fast and easy. It's basically to make sure you have the basic concepts of torque down and how to find them, and rotation. The problems in homework 7 are a bit tough. They're tougher than probably, well, they're not all tough. A couple of them are super easy. A few of them are tough, and they're tougher than the exam problems, but that's intentional, because if you can do them, you'll be fine on the exams. The last two that have to do with elasticity are way harder than what I would ask you to do, but the log one is a really good equilibrium and elasticity problem. In my announcement, I talked about, I totally apologize. I started doing the solution and it was like the last one I had to do, and I was tired, and I totally forgot that I had to add a little thing to it, which I did. But like the first part of that is, that final question is pretty much useless because I forgot how to solve it. And then I reminded myself by looking at the solution. But other than that, if you guys have problems, let me know. I'll try to clarify anything I can. And then remember too that tomorrow you need to be able to Zoom with me with your camera on. That all being said, any questions before we call it for the day? I'm all good.
I have a question about the solution for problem 2 on the second exam that we were looking at. For the energy problem.
Did I mess that up? I might have messed that up. So can you see your screen?
Yeah.
Okay, so you're talking about this one right here?
I think it was on the other exam.
All right, let me pull that up. So that would have been, I don't know which one I just opened. I thought the other one. Let me make sure I didn't. Did I just open the same one?
No, I think this is the one I was talking about.
Oh, yeah. What's the question?
Yeah, so problem 2, part D, with like the solution had IAB omega squared over 2, but I was wondering if it should be multiplied by 2.
It absolutely should. I dropped a 2, and I am notoriously bad about doing that. There should be a 2 here, and so I don't know if this solution is even right, which is weird because it should have gotten them back. I should have caught it because this solution should be the same omega or V as the previous one. So I don't know, maybe the only thing I can think of is that I might have copied this from really sloppy work I did on scratch paper. But yeah, you are absolutely right. There should be a 2 here. What she's asking is, shouldn't there be a 2 here? And there should be a 2 here because this problem was the one that had a pulley on the left and on the right, and they look exactly the same. That's also why you're getting 2 in front of this M here. But yeah, hopefully hopefully it didn't go through. I see that it's actually not right there either, and it should be there. But yeah, you're absolutely right. It should have a 2 in front of that IAB. Any other questions?
Do you have any recommendations for like collision and like elasticity questions that you might ask for the exam?
The one that's on here, and I don't even know if it's on this exam. It's not on the other exam. To be honest, so on this one, unless this is the wrong one, I really should have named these better. So yeah, on this one, this is the second one that doesn't really have a number. When it talks about this part right here, if you know how to do that, you're fine. But look at the last two homework problems of homework 7, and they're both elasticity. One's a tunnel, so it's a little weird because they want you to do some weird stuff on that. I would not worry too much about that one. But the one with the log that's being held by the two different wires, that's a really good elasticity problem. But if I ask you something with it, it will be straight up plug and chug like this. Plug some numbers in and get whatever out. You guys should know by now that I like you to compare things. So in this example, you're finding delta L and comparing it to a number. And if it's more or less, then it tells you, did the wire break or did it not break? But that's about it. As far as the equilibrium stuff, make sure that you study the examples in the book. Let's go to this module, textbook study. Just go to chapter 12 if it'll ever open. Equilibrium, if it will ever open. I don't know why it's not open. Examples of static equilibrium. This guy right here. So if you go through this example right here, and make sure you know this one, you're good with those kinds of static equilibrium problems. I believe your book may or may not have a scaffold type one, but there will be interactive exercises on there. Center of mass versus center of gravity. Just take a look at some of these if you really need help with those. But yeah, if you understand the latter example, you're good for equilibrium, to be honest with you.
And then the homework one, and then for the collision, you just do the homework, right?
Oh, I'm sorry. For the collisions, so the funny thing about collisions is if we go back to this thing, you have to know the difference between an inelastic and an elastic collision. And if you know that, basically if they bounce off each other, they're elastic. And we always assume one of them is at rest. So elastic collisions, you then can find that after the collision, the velocities from these two equations. And basically you can find the change in kinetic energy is 0, but you could find the kinetic energy before and after. This is always true. Whether it's elastic or inelastic, the momentum before and the momentum after are equal. You can see that. Inelastic means they stick, and that's how you remember it, is the final velocity is both the masses together, or the final momentum of both the masses added together times the final velocity. However, the thing you have to remember is you cannot set mva squared over 2 plus mbvb squared over 2 is equal to ma plus mb final squared over 2. These are, the kinetic energy is not conserved. And so really all you have is, you have either this equation, and then you could find the final kinetic energy or the initial kinetic energy. But that's all you have for inelastic. For elastic, what you do is you typically are given the initial velocity and you need to find the final velocities. And that's all that depends on is their masses. So just do a couple of look up, Google inelastic, elastic collision. And if you understand them, you're good. There's not a lot to do there. They're really simple. Out of the collision though, also understand the impulse thing. And that's that if an object collides with like a wall and bounces off, or a baseball is hit by a bat, we can find the change of momentum, mv, this right here, is equal to the force times the time. And so we did quizzes on those. Make sure that you understand those quizzes. Go back and look at the solutions to those if you need to. I think those are relatively simple problems though to understand mathematically. There's not a whole lot of meat on them. And there's nothing you really need to do as far as like a drawing or a diagram. You just need to understand the initial momentum is the final momentum and whether or not the kinetic energy conserved. And that's really all. Anything else you had questions on? If not, we're going to end. Good luck to everybody. I'm going to finish off the test today and get everything ready for tomorrow. If you have any questions or you catch any solution mistakes, let me know and we'll fix them. Other than that, I hope everything's going well. I hope you're all well, and I hope you're all semi-prepared for this one. This is a hard exam. The next exam's easy. Torque always throws people, so if you're feeling a little confused, just practice the equilibrium ones until you feel like you have torque down, and then go and look at the energy torque, the pulleys and masses, and see if they make more sense after you do equilibrium. Otherwise, I'll talk to you all later. Thanks for coming to the meeting. See you soon.
Thank you. Have a good day.
You too, guys.